Hello, everyone. Welcome to Physics Lab. So this is the video lecture for Lab 1, which is on measurements and vectors. And in particular, we'll talk a lot about how to compute percent experimental error, percent experimental accuracy, which is a measure of the variability. And we'll also talk about how to add vectors together. In particular, how to add them experimentally and then graphically. So using a protractor and ruler, we'll also add them graphically. Now this lab is very similar for all three of the labs that I teach, Physics 206, 207, and 212. So I'm just gonna do this one video. The only difference is there's a few sections that Physics 206 does not have to do, and I'll let you know when we get to those sections. So if you're in Physics 206 and you're watching this, there's a few sections that you won't have to do. Okay, but Physics 207 and 212, everything else is gonna be identical for your two classes. Okay, so the first thing that I wanna do is I actually wanna go to the measurement handout. So this is sort of like part B of that measurement handout, and talk about accuracy, precision, the resolution of an instrument, all those type of things. So let's go to that handout now. Okay, so I want to start off by explaining the difference between accuracy and precision. So if you look at the definition here for accuracy, it's the degree of closeness of measures of a quantity to the true value of that quantity. So you're comparing the average of your experimental values to like the gold standard or the accepted, or sometimes you say predicted value, okay? So in this class, the accuracy is going to be measured by something called the percent experimental error. And I will show you guys how to compute the percent experimental error in a little bit. All right, so that's accuracy. Now, precision is the degree to which repeated measurements show the same results. So in some ways, it's sort of a measure of the variability. Like if you take 5 measurements or 10 measurements, right? They're not necessarily going to all be the same. There's going to be some variability, and we want to measure that variability. That's what the precision tells you. Now in this class, we're going to measure the precision by using something called the relative average absolute deviation. Okay, and again, I will describe how to do this. We'll go through a couple of examples of this. Now here's the confusing part. The lab manual, which was originally written 1970-ish, when they refer to this as the percent experimental accuracy. So they refer to the relative average absolute deviation as the percent experimental accuracy. So it's a little confusing because it's really a measure of precision, right? Even though it's called percent experimental accuracy, it's a measure of precision. But we're kind of stuck with that terminology. And in many of the labs, I ask you to compute percent experimental accuracy. And if you look at the lab manual itself, many of the questions ask you to compute it. So just keep in mind that when it asks you to find the percent experimental accuracy, you're really measuring the precision, right? You're calculating this relative average absolute deviation to measure precision. Now the resolution is the fineness to which a measuring instrument can be read. So you can think of it as basically like how many decimal places you can read an instrument to. So in other words, if I told you that I did a measurement with a vernier caliper and it was 5.35 centimeters, then that would be 2 decimal places. So therefore, you could say that the resolution of that vernier caliper was 0.01 centimeters, right? Because it's 2 decimal places. So 0.01 would be the smallest you could read, like 1/100th would be the smallest that you can read, or 1/100 centimeters. Okay. One nice way of explaining the difference between accuracy and precision is using this bullseye diagram. So if we look at this case, the upper left-hand case, if you average the location of these, so think of the black dots as sort of your data, right? If you were to average these, it's probably like here somewhere. So it's not really in the center. So that means it's low accuracy, right? Because the average is not like the gold standard should be right in the center of the bullseye. So since it's not right in the center, you have low accuracy. And then you also have low precision in this case. Why? Because these values are distributed a lot, right? There's a lot of variability here. They're not clustered together, right? So this would be an example of low accuracy and low precision. If I go to the upper right, here is an example, definitely a low accuracy because the average is, say, out here somewhere, right? If you average those 6 values and you want the gold standard is right here, so low accuracy, but high precision because all the values are almost the same and they're tightly clustered, right? There's not a lot of variability. So high precision. In the bottom left, this would be high accuracy because the average is pretty much right in the center, but low precision because there's still a lot of variability, right? They're not clustered very well. And then finally, sort of maybe the best case would be high accuracy where the average is right in the center of the bullseye and they're all clustered. There's not a lot of variability. They're really tight. All the values are nearly the same. So that would also be high precision. So high accuracy and high precision. Okay. So let's first talk about, and I think this is the one that's a little more difficult, takes a little longer to explain, calculating percent experimental accuracy. Now remember, even though it's called percent experimental accuracy, this is a measure of precision, right? It's a measure of the variability. It's that relative average absolute deviation. That's what we're going to be calculating. So in this example, and I'll do this on the iPad so I can work it out bit by bit. But let me explain the example first. So I want to measure the area of some large rectangular plate or something. And I take 10 measurements of the length and 10 measurements of the width, okay? Let's say I want to compute, and you can see there's some variability here, right? These aren't all the same. There's some variability in the length measurements. There's some variability in the width measurements. I want to compute the percent experimental accuracy to look at the variability in the length, right? Remember, it's a measure of precision. And I also want to compute the percent experimental accuracy to look at the variability in width. And then later, I will want to compute the percent experimental accuracy for the area itself, okay? So let's start with length. So these are my values for the length. And let me write these down on the iPad and I'll continue from there. Okay, so I have 10 measurements of the length. Let me write down those measurements. So length, which is in centimeters, I have 8.2, 8.1, 8.0, 8.2, 8.3, 8.1, 7.9, 8.0, 8.4, and 8.2. Okay, so the first thing you want to do is you want to recognize the resolution of the instrument. So whatever was used to measure the length, we can see that its resolution is 1 decimal place, right? So our best guess, just by looking at the data here, is that the resolution of this instrument, I'll write it over here somewhere. Maybe it was a meter stick or something, is going to be 0.1 centimeters, right? Because everything is to 1 decimal place. So the resolution is 0.1 centimeters. All right, let me go back to the data. So the first step in calculating the percent experimental accuracy is to compute the average of this data. So if you add up all those values, right, and you divide by 10, you come up with, I think it's 8.14, but then you want to round to the resolution of the instrument, which is 1 decimal place. So the average here, so I would get 8.14, but then I need to round to the resolution of the instrument, which is 8.1. So I'm finding the average length by averaging them and rounding to the resolution of the instrument. Okay, next I have a second column, and these are what's called the absolute deviations. also in centimeters. And what these are is how far each data value is from the mean, from the average. So in other words, my first data value is 8.2, right? So if I want to find the absolute deviation, then I need to do 8.2 minus the mean, which is 8.1, absolute value. So 8.2 minus 8.1 is 0.1, and then absolute value 0.1 is going to be 0.1. Then the next value, I have 8.1 minus 8.1 absolute value. That's going to be 0.0, right? 0, absolute value 0 is still 0. Then I have, say, I'll do one more, 8.0 minus 8.1. Well, that's negative 0.1, but then when I take the absolute value of that, I'm going to get positive 0.1. So these absolute deviations are always going to be non-negative, right? They could be 0, or in most cases, they're going to be positive. They'll never be negative because you're taking absolute value. And usually what you can do is you can sort of do this in your head, right? So next one is 8.2. How far is 8.2 away from 8.1? It's 0.1. Then 8.3 away from 8.1 would be 0.2. Then 8.1 away from 8.1 is 0 again. 7.9 away from 8.1 is 0.2. 8.0 from 8.1 is 0.1. 8.4 away from 8.1 is 0.3. And then 8.2 from 8.1 is 0.1. Okay, so I have all of my average absolute deviations. Now what you want to do is you want to average those absolute deviations. And again, you want to round to the resolution of the instrument. So if we average those values, we're going to get, I think it's 0.12. So if I average these, I'm going to get 0.12. But then I need to round to the resolution of the instrument, which remember was 1 decimal place. So this is going to be 0.1. So this is called, move this up a little bit. This is called the average absolute deviation. Okay, now the last step to calculating percent experimental accuracy. So now I want to find the percent experimental accuracy for length. To compute that, I take my average absolute deviation, which is 0.1. I divide by my average length value, which is 8.1, and then I multiply by 100 just to make it a percent. And if you do that, you're going to get around 1.2%. This would be 1.2%. So that's it. It's always going to be your average absolute deviation divided by your average value, in this case, your average length, times 100. That's how you compute the percent experimental accuracy. Okay, so if we go back to the handout. So in this case, I computed the percent experimental accuracy for length. I got 1.2%. Let's say I do the same thing for width, right? So I average these 10 width values. I round to the resolution of the instrument. That gives me 3.2. Then I find all the absolute deviations, right? So how far is 3.3 away from 3.2? It's 0.1. How far is 3.3 from 3.2? 0.1. Then 3.2 is 0 away. 3.3 is 0.1 away. 3.0 is 0.2 away, and so on. Then I average these absolute deviations. I round to the resolution of the instrument, which again is 1 decimal place. It turns out it's again 0.1. And then finally, how do I find the percent experimental accuracy for width? I would take the 0.1 and divide by my average width, 3.2, times 100. So that's done here. Remember, it's always the average absolute deviation, so 0.1, divided by your average value, in this case, your average width, times 100. And that gives me 3.1%. Okay, now the next thing that you might want to do is you might want to compute the area, right? The area of this rectangular plate. We know the length, we know the width, right? We have the average length, we have the average width. So therefore, what you can do is just, we know the area of rectangle is length times width, right? So I can take my average length value times my average width value, multiply them together. In this case, I get 26. And then of course, centimeters times centimeters gives me units of centimeters squared. So my area of the plate would be 26 centimeters squared. Now notice here I was being careful with significant figures. Since the length had 2 significant figures, the width had 2, my answer for the area could only have 2 significant figures. However, in general, when you guys are writing up your lab reports, I'm not going to worry too much about significant figures for the final answer. So if you give me like 1 or 2 decimal places, that will be fine. I'm not going to worry too much about sig figs, okay? The only thing that's really important when you're doing calculations is when you compute percent experimental accuracy, like up here, when you round the averages and round the average absolute deviations, these have to be correctly rounded to the resolution of the instrument. But when you compute the final percent experimental accuracy, if you gave me like, another decimal place here, I'm not going to worry about that too much. Okay, so just be aware of that. Just worry about rounding to the resolution of the instrument when you're computing percent experimental accuracy. But final answers, don't worry too much about sig figs. Okay, now there's one other thing that we have to talk about, and let me go back to the iPad to do this. Okay, so we found the area. Remember, the area was simply going to be the average length times the average width, right? What if I want to compute the percent experimental accuracy for area? How do I do that? How do I find the percent experimental accuracy for area? We know the percent experimental accuracy for length. We know what it is for width. Well, how do I combine those together? How do I combine the accuracies to get the accuracy for area? Well, notice here that in this formula, right, we want to find the percent experimental accuracy of the area, which is sort of our dependent variable. It depends on length and width. And what's happening to the length and width? Well, the length and width are being multiplied together, right? It's length times width. They're being multiplied together. So the rule is, if you want to compute the percent experimental accuracy for the dependent variable, in this case, the area, and that variable involves multiplying or dividing a bunch of variables together, the rule is you have to add the respective percent experimental accuracies. So here, let me write out the formula. It's a little confusing, but let me write this out. So if I want to find the percent experimental accuracy for area, since my formula for area involves multiplying length times width, that means I have to add the percent experimental accuracy for length plus the percent experimental accuracy for width. And whenever you have an equation that involves multiplying or dividing variables, you're basically going to add the respective percent accuracies together to give you the percent experimental accuracy of the dependent variable. Okay, and really that's the only case that we're going to deal with in this particular lab. We may have to add them together. The reason why you do that comes from calculus. It's sort of like a worst case scenario, right? Like if I have, let's say I have a rectangle and let's say, I make an error on the length. So let's say this is length and this is width. And I make an error on the length of that much. And then same thing for the width. You can ignore this little small rectangle there, then basically if you add those two accuracies together, it gives you the percent experimental accuracy of the whole thing. Right, so it's sort of like a worst case scenario, you're adding the two errors together. So really all you have to remember is if you add the respective percent experimental accuracies, you'll get the correct value. Okay, so let me go back to the handout. Okay, so in this case, remember the percent experimental accuracy for length was 1.2%. The percent experimental accuracy for width we calculated as 3.1. So if I add those two together, I'm going to get the percent experimental accuracy for area, which in this case is 4.3%. Okay, great. So that's percent experimental accuracy. Now, the other type of sort of error calculation that you're going to be making many times throughout this course in many of the labs is something called percent experimental error. And again, this is when you want to compare your experimental value, sort of like your average experimental value, to a predicted or gold standard or accepted value. I kind of use those three words interchangeably: predicted, accepted, gold standard, sometimes theoretical. So you're comparing your experimental to what you think the true value is. And remember, again, it's confusing because this is now a measure of accuracy, right? When you compute percent experimental error, it's really the measure of accuracy when you're comparing your experimental value to a gold standard. Okay, so one of the things that we're going to do in this part of the lab, and I'll give you guys all the data for this, is you're going to measure the density of a small aluminum cylinder. So let's say you go through all the calculations and you find that the density experimentally is 2.6 grams per centimeters cubed. And then you're told that the predicted or accepted value, let's say you look this up, you know, in some type of handbook or on Google or something, and you're told that the accepted predicted gold standard value for the density of aluminum is 2.7 grams per centimeters cubed. So you want to see how close your experimental value is to the gold standard. So that's when you would compute the percent experimental error. This one's much easier to calculate. All you need to do is the following. In the numerator, you would subtract the values. Now, I have it written as experimental minus predicted, but it doesn't really matter because you're going to take the absolute value. You're going to make it positive anyways. So I usually just say subtract largest minus smallest, right? If you want, you can think of it as experimental minus predicted, but then remember you have to do absolute value. But then in the denominator, you want to always put the predicted, accepted, gold standard value. And then times 100, and that will give you your percent experimental error. So in this example, we had, say 2.6, right, was our experimental value, minus the gold standard, 2.7, but then absolute value, so that'll be 0.1. I divide that by 2.7, so I did it down here, and then times 100, and that will give me a percent experimental error of 3.7%. Okay, and the lower the better, right? The lower means it's closer to the gold standard. Now, here's a subtle point. For percent experimental error, it is okay to get 0%. It's okay to compute 0%. That just means you got exactly what the gold standard is, right? Your experimental value was exactly the same as the gold standard value or the predicted value. Like in other words, if we had gotten 2.7 here instead of 2.6 as our experimental value, we would have calculated 0% for percent experimental error. So that's fine. But it turns out that when you compute percent experimental accuracy, right, which is the first thing that we did earlier, which is the measure of precision, the variability, you can never have 0% because we always assume that there's some error associated with the instrument itself, okay? Let me go back to the iPad and explain that a little more carefully because this could come up in this lab and it certainly will come up in some future labs. Okay, so let me explain what you should do if you're going to get 0% for percent experimental accuracy. Remember, we cannot have 0%. So let me explain how you would handle that. Let's say I'm measuring, actually, since we're talking about the cylinder, let's say I measured the height of the cylinder 5 times. And let's say I get these values, 5.35, 5.35, 5.34, 5.35, 5.35. Right, so those are my 5 values. And I want to compute the percent experimental accuracy for height. Okay, so remember the first step is I need to round these, right, round these 5 values and round to the resolution of the instrument, which in this case is 2 decimal places, right? The resolution of this, we're going to use a vernier caliper, is going to be 0.01 centimeters, right? That's the resolution, because there's 2 decimal places. Well, if you average these 5 values, you're going to get, I guess it's 5.348, right? And if I round to 2 places, that gives me 5.35. Right? So that's my average height, 5.35. Remember, the next step is I create that second column of absolute deviations, which are also in centimeters. And they represent how far each data value is away from that mean. So how far is 5.35 away from 5.35? It's 0, right? And actually, if I'm being really careful, I'll write this as 0.00. The next one is also 0.00. Then 5.34 is 0.01, right? Then 0.00, then 0.00. Okay, then our next step was to round these absolute deviations to average these absolute deviations and round to the resolution of the instrument again. So if we round these, if we average these, we're going to get 0.002, right? And if I round that, I'm going to get 0.00. If I round the 2 places, it's just 0.00, right? The 2 drops off because it's less than 5. Now here's the problem. If I go ahead and try to compute the percent experimental accuracy now, I'm going to have 0 divided by 5.35 times 100. That's going to be 0%. And we just argued that we can never have 0% when we calculate or compute percent experimental accuracy. So what do I do in this case? Well, here's the solution. Whenever this average absolute deviation here, whenever it's less than the resolution of the instrument, you have to default or use at least the resolution of the instrument for that value. So instead of 0.00, I have to use at least 0.01. So whenever it's less than 0.01, you have to round up to 0.01. If it's greater than, then you just use whatever value you have, right? It just means you have more variability. But if it turns out it's less than the resolution of the instrument, you have to use at least the resolution of the instrument there. And now we can continue, right? So now the percent experimental accuracy for height would be I'd use the 0.01 now, divided by 5.35 times 100. And if you work that out, I think it's around 0.19%. So less than 1%, which is great. By the way, it sounds backwards, right? But the lower the percent accuracy, the better, because it means that there's less variability. So you want that number also to be small. And it's not 0. Right now it's not 0, because remember, it can't be 0. And we fix that by making the average absolute deviation at least the resolution of the instrument. Okay, so that's how you handle that situation. Okay, so let's just discuss the last page of this measurement handout. So again, ultimately our goal is to measure the density of a small aluminum cylinder, right? Let's say we measured the volume of that cylinder and we found it to be 5.34 centimeters cubed. And this is the percent experimental accuracy for the volume, 3.4%. Right? So there's our volume. Now, how do I compute the density of something? Well, the density is going to be the mass divided by the volume, correct? So I need to mass the cylinder. So I did that on an electronic scale, and I'll give you guys that data. Let's say in this case, my mass was 13.9, 13.9, 13.8, 13.9, 13.9. So notice one thing here. First of all, the resolution of this scale now is 0.1 grams, right? Because if you look at the measurements, it's only accurate to 1 decimal place. So the resolution is 0.1 grams. So if I wanted to compute the percent experimental accuracy for mass, I average these, round to the resolution, so that's 13.9, find all my absolute deviations, so 0, 0.0, 0, 0.1, 0, 0.0, 0.0, average these, right, which I'm going to get 0.02, but then I need to round to the resolution of the instrument, which is 0.0, but then remember I have to argue, well, I can't use 0 or 0.0, I have to use at least the resolution of the instrument, so I have to use 0.1. So now when I calculate percent experimental accuracy for mass, it'll be 0.1, which is here, divided by my average mass times 100, so 0.72%. Okay, now that I have my average mass and my average volume from above, I can compute the density, right? So the density is going to be mass divided by volume. In this case, I get 2.6 grams per centimeters cubed. And then if I wanted to compute the percent experimental accuracy for density, since this equation involves dividing two variables, remember, whenever you have an equation that involves multiplying or dividing variables, and you want to compute the percent experimental accuracy for that dependent variable, the rule is you add the respective percent accuracies for the variables. So percent experimental accuracy for density is simply going to be the percent experimental accuracy for mass plus the accuracy for the volume. In this case, the accuracy for the mass we computed to be 0.72%, the volume was 3.4. If I add those together, that's going to be the accuracy for density, 4.12%. Okay, so it's sort of just a review of what we talked about. Okay, let me go to the lab handout now. Okay, so remember the first part of this lab is to measure the density of that small aluminum cylinder. And we want to make the measurements of the cylinder with a vernier caliper. We need to compute the volume of the cylinder. So we need to find the height of the cylinder and the diameter of the cylinder. Now, the question is, how do we read a vernier caliper? Now, of course, because of the situation where you guys aren't collecting the data yourselves, I give you all the data here, but let me describe how you actually read a vernier caliper. Now, one thing you can do, I created a brief video that you can watch. So if you go to this link right here, or I describe it, and there's also a simulation. So actually, I'm gonna go to the simulation right now and kind of explain how you read the vernier caliper. Okay, so here's the vernier caliper, right? You have the object between the jaws. Actually, let me make the object a little bit bigger. Say something like that. And you would close the jaws on the object, right? So in our case, it'd be the height of the cylinder and the diameter of the cylinder. Now, there's two scales here. You have a main scale on the vernier caliper, which is in centimeters. So that's the 0 through, probably goes through like 6 or something. Right now, you can only see 0 through 4. So that's the main scale in centimeters. And then you have this vernier scale, which goes from 0 to 10, really 0 through 9. So that's the vernier scale, right? And it's on the slider itself. Now, when you're reading the length of this object here that's between the jaws, what you're doing is you're reading where the 0 on the vernier scale is. So this is also called the index, the 0 here, where it's located on the main scale, right? That's the whole goal. You're reading where the 0 is on the main scale, its location on the main scale. So if you think about this, right? See how the 0 is just past this mark right here, and this would be the 0.7 mark. So this is going to be 0.7 something, right? So the question is, how do we get that next digit? How do we get the second digit? Well, just eyeballing it, since it's only a little bit past the 7, it might be like 0.71 or 0.72 or 0.73, just a little bit past, right? To get that directly, exactly, I look on the vernier scale and I ask myself which line on the vernier scale lines up best with any line from the main scale. And probably in this case, I would argue that the second one lines up best. So then you would read this as 0.72 centimeters. And that's what we have. Actually, the answer is over here. If you want, you can even, there's a hint here. If you do hint show, it'll kind of tell you, okay, you're past the 0.7. and then it's telling you that the two lines at best, so you're adding an additional 0.02, so it's 0.72. Okay. Hint off. Here, let's do another one. Let's say this is the object. So what does that read? Don't look at the answer. Let's see if we can figure this out. So where's the 0 on the main scale? Well, the 0 is, this is 1, right? 1.1, 1.2, 1.3, 1.4. So it's 1.4 something. Kind of looks like it's around halfway. So it might be 1.44, 45, 46. To get that last digit exactly, I look on the vernier scale and I ask myself which one lines up best. Sometimes it's hard to tell. In this case, it looks like the 5th one lines up best. So I would say the reading is 1.45 centimeters. And that's what it's telling us, 1.45 centimeters. Okay. If the 0 were right on, let's say this is the object. Oh, let's see if we can do it exactly. Let's say that were the object, right? So this would be, where's the 0? It's on the 1.5, and then the 0 lines up best, right? Because it's right on it. So you would say 1.50 centimeters. Remember, since the resolution of this instrument is 0.01, you always need 2 decimal places. So you'd have to put that 0 at the end. So 1.50 centimeters. Okay, so that's how you read a vernier caliper. So you might want to just play around with that, practice it, and see if you're getting the correct answer here. Okay, so in the first part of the experiment, I give you a table of values. So 5 values for the height, 5 values for the diameter, right? So we're assuming a vernier caliper was used and the resolution is 2 decimal places, 0.01 centimeters, right? It would be the resolution. So what I want you to do, for question 1, is compute the average height and average diameter. Again, make sure you round to 2 decimal places, right? Round to the resolution of the instrument. And then compute the percent experimental accuracy for the height and the accuracy for the diameter, right? So compute these percent experimental accuracies. And I gave you enough room in the table here so you can do your absolute deviations and your average absolute deviation. And then make sure you show me those 2 calculations for the percent experimental accuracies. Okay, you don't have to show me the calculations for the average. I'm assuming you guys can all do the averages. Just make sure you round it correctly. But show me the calculations for the percent experimental accuracy. Now, to help you guys out for the first lab, I created a sample lab report for lab 1, which gives you a really good idea of what I expect for your particular group lab reports. Okay, and we can look at that later. All right, once you've done that, I want you to compute the volume of the cylinder. So the volume of a cylinder is pi r squared times the height, where r is the radius. But in this case, since we're measuring the diameter, instead of using r here, I just rewrote the formula in terms of diameter. We know that the diameter is twice the radius, or the radius is half the diameter. So if you plug in d over 2 and you work it out, this is exactly the same formula. So you want to use this formula right here because it involves diameter and height. So you're going to plug in your average diameter, plug in your average height, and work this out, and that'll be your volume of the cylinder. Then I want you to compute the percent experimental accuracy for volume. Well, remember, if I want to compute the percent experimental accuracy for a dependent variable, if it involves multiplying or dividing variables together, I have to always add, right, the respective percent experimental accuracies. So forget about the pi and the 4. They're exact values, right? They're not variables, so you don't have to worry about those. But here I have diameter squared times height. So you can think of this as diameter times height. So if I want to compute the percent experimental accuracy for the volume, I have to add the percent experimental accuracy for the diameter plus another one, because it appears twice here, plus the percent experimental accuracy for height. So to get this value, basically you're going to add the accuracy for diameter plus another one, right, or 2 times if you want to do it that way, plus the accuracy for height. So it'd be this plus another one plus the accuracy for height. and that will be your percent experimental accuracy for volume. Okay, and again, it's just because the formula involves multiplying those variables, so you have to add the respective percent accuracies. So question 3, I give you the data for the mass of that aluminum cylinder. So I want you to compute the average mass and then also find the percent experimental accuracy for the mass. And remember, in this case, the resolution of the balance is 0.1 grams. So you have to round this to one place and round this to one place. And it may be the case where you have to use, 0.1. You have to use the resolution of the instrument here for your average absolute deviation. Once you've done that, question 4 is compute the density of your aluminum cylinder. So given my data, right, it's experimental data. How do you do that? Well, you use your average mass from this table, right, the average mass divided by your average volume from a previous table, and that will give you the density. Then you want to compute the percent experimental accuracy for density. Well, again, since the formula involves dividing these variables together, then you have to add the respective percent accuracies to get the accuracy for density. So it's just going to be your percent experimental accuracy for mass plus the accuracy for volume. If you add those two together, then that will give you the accuracy for density. Okay, and that'll go here. And finally, compute the percent experimental error. That's when you compare your value, your experimental value, to the gold standard, which in this case we're going to say is 2.7. Okay, and if you forgot some of these things, you have to look back at those other handouts. Plus, my sample lab report will also kind of help you, remind you how to do all these calculations. But you want to make sure you show all the calculations, right? And you always want to give me the tables. What I would do is go to my Word document. I have all these posted on Brightspace, and copy and paste the table into your lab report, right? So you'll have all that data, and you want to fill in the tables. Of course, some of the data is already there, right? Some of the experimental data is already there. Okay, so that's it for the measurement part. So finding the density of that small aluminum cylinder. So we talked about computing percent experimental accuracy and error, and how to read a vernier caliper. The next part of the lab is the addition of vectors. Okay, this is kind of like 2 labs in one. This is sort of how this year is going to go. Again, it's because only half of the people can actually come to lecture when I talk about all these things. So it's kind of, I'm giving you like 2 weeks, but you're basically doing like 2 labs in one. Okay, so let me remind you of what a vector is. Hopefully you'll be talking about some of this stuff at about this time in lecture, so you'll hear a little bit about this. So a vector is a quantity that has both magnitude and direction, and many of the things that we talk about in mechanics are represented as vectors. Things like positions, velocity, acceleration, forces, which is what we're going to talk about in this lab, torques, etc. Those are all things that have both magnitude and direction, and they can be represented as vectors. Now, usually when you write down a vector, it's either done, typically in a textbook, you might see a bold-faced letter, so that would represent the vector F, or if you're handwriting it, you usually put an arrow above the letter, so this would be also vector F. So it's either a letter with an arrow over it, or it's in bold. Usually if it's in the textbook, they bold it. Sometimes they do both. Okay, so those both represent the vector F. Graphically, you can think of a vector as an arrow, right? Like a directed line segment or an arrow. So in this case, I have my Cartesian coordinate system, right, or my XY coordinate system, and I have a vector that's drawn from the origin, so this is like the tail of the vector, to the tip, so the arrow is going out this way. This represents the vector F. Now the magnitude is going to be the length of this arrow. So the length of the arrow represents the magnitude of the vector, like it's 10 newtons or 15 pounds, whatever the units are for force, right? We're going to use newtons mostly in this particular class. So let's say it's 10 newtons. But that doesn't quite, 10 newtons doesn't give us quite enough information. We also need to know the direction. So if you have the vector drawn with respect to a Cartesian coordinate plane, then I can read off the angle, and it's by convention, we always measure the angle from the positive x-axis counterclockwise. So this angle theta would give me the direction of that vector. So it might be, 10 newtons at 30 degrees or something like that. So a vector has both magnitude, its length, and direction is given by this angle here. Okay, what if we want to add two vectors together graphically? That's what we're going to really focus on in this particular lab, is adding vectors graphically. So in this example, I have vector A. It has a magnitude, right, whatever that length is, and it has a direction, whatever that orientation is, right? If you drew a coordinate system here, you can measure the angle, and that would give you the direction. And then B has a length, and it has a direction, right, defined by the arrow. And again, you could measure the angle if you wanted to. Now, the thing about vectors is really it's only the magnitude and direction that are important mathematically to vectors. It doesn't matter where they're located. You can move them around. If you move this around, as long as you maintain the same length and the same orientation, the same direction, you can slide it around and it will be the same vector, right? Mathematically, you can think of it as exactly the same vector. So if I wanted to add these two vectors together, there's a couple of different techniques that we can use. And the one that we're going to focus on is called the triangle method. You can think of it as sort of the tip to tail method. And what you do is you start by taking that first vector, so in this case, vector A, and I'm going to slide it so that the tail of A is at the origin of my coordinate system. So I just slid it down, right? It has the same length, the same orientation, but now the tail is at the origin of the coordinate system. Then I take my second vector, vector B, and I slide it down, maintaining the same length and same orientation, so that the tail of B is at the tip of A. And then finally, if I draw a vector from the tail of the first vector, so from the tail of A or from the origin to the tip of the second vector, which is right here, that's going to be what we call the resultant vector, which is A plus B. So this is the sum. The resultant is the sum of A and B, the sum of these two vectors. Now notice that the resultant has a magnitude, it has a length, and it has a direction, which you could figure out by measuring this angle here. Okay. The reason why this is called the triangle method is typically when you add two vectors together like this, the resulting figure is going to end up being a triangle. All right, another way you could add two vectors together is called the parallelogram method. We're not going to use this as much in lab. You might see it in lecture a little bit. We're going to use mostly the triangle method. But let me just mention this briefly. So in this case, what you do is you slide both vectors so that their tails are at the origin. So A, its tail starts at the origin, and B, it also starts at the origin. And then basically I complete a parallelogram. I draw a side that's parallel to A and the same length over here. So I have it dashed in here. So this is parallel to A and it's the same exact length. Then I draw a side parallel to B in the same length. So it's dashed in here. So I get this parallelogram. And then finally, if I draw a diagonal from the origin to the opposite side of the parallelogram, that's going to be the sum of those two vectors, A plus B. But notice here that you can kind of see the triangle method sort of in here, right? This is sort of A, and then you can think of this as the tail of B. So here's B, and when I add tip to tail, I get R. But notice I could start also with B, and then this is basically A, add tip to tail, and I also get R. So the nice thing about the parallelogram is you can see that the order in which you add vectors doesn't matter, right? A plus B is the same as B plus A. You get the same resultant vector, okay? All right, now, so that's if you're adding two vectors together. You can either use triangle method or parallelogram method. If you're adding more than two vectors together, let's say three vectors, then you want to use what's called the polygon method, but really it's nothing more than adding tip to tail. You just keep going. You keep adding tip to tail. So in this example, right, I start with A. Let's say I slide it so that the tail of A is at the origin. Here's the tip. Then I slide B so that the tail of B is at the tip of A. Then I slide C so the tail of C is at the tip of B. And then finally, if I draw a vector from the tail of the first, so from the origin, right, the tail of A, which is at the origin, to the tip of the last one, in this case, the tip of C, that's going to be my resultant vector. That's going to be A plus B plus C. And again, the order doesn't matter. If I had started with, C, which would have gone this way, and then B, and then A, I would have got exactly the same thing. You'd find it doesn't matter which order you add these, you're going to get the same result. Right? It doesn't matter how you add them tip to tail. Okay, so hopefully that made sense. I will talk more about this when we talk about some of the questions itself, like how to add these things graphically. So in this experiment, what we're going to do is we're going to measure, or we're going to compute the sum of two forces two different ways. We're going to add them experimentally using the Kennan force platform. And then we're going to add them graphically using protractor and ruler. Okay, so first thing you want to do is you want to click on this link here and go watch the short little video I created on how to use the Kennan force platform to add two force vectors together. Okay, so you want to watch that where I describe exactly how you're going to do this. If you go to class this week, if you happen to be in class, and I will describe this in class, but if you're doing this remotely, then you want to make sure you watch that video. So let's say that we hung mass 1 at 30 degrees. Let's say the magnitude was 100 grams. Okay, and then mass 2 was at 120 degrees and it's 200 grams. And then I balance it, and again, this will make more sense when you watch this video here. I balance it by finding the equilibrant, and that turns out to be 230 grams at 273 degrees. Okay, so what I want you to do first is I want you to convert the masses to forces, because really we're talking about vectors here. So we need to be talking about forces, right? A mass is not a vector, it's a scalar. It doesn't have a direction, it only has a magnitude. So really what we want to talk about are the forces, which happen to be the weights, right? We're going to get the force by computing the weight given the mass here. Actually, let me jump on the iPad to show you how to do that part. Okay, so we know that if we want to compute the weight, which is really like the gravitational force of those hangers, that's going to equal the mass, and then we have to multiply by g, which is the acceleration due to gravity, or some people call it the gravitational field constant. Think of it as just the acceleration due to gravity. But to do this in the correct units, I want my weight to be in newtons. So that means the mass has to be in kilograms. And then we can use the SI units for G, which we're going to use 9.8 meters per second squared. Okay, so let's say, I'll talk about the first force, F1. That was 100 grams, right? But first, I need to convert that to kilograms. So I can either move the decimal point 3 places to the left, right? That'll make it kilograms. Or if you want to multiply by a unit conversion factor, I can say 1 kilogram over 1,000 grams, right? And that, when I multiply by 1 over 1,000, that's the same thing as moving it 3 places to the left. Then, so now it'll be in kilograms, and if I multiply by 9.8 meters per second squared, that'll give me the correct result. So grams will cancel, right? And then it turns out kilograms times meters per second squared has a special name. First of all, if you multiply it out, you're going to get 0.98, and that special name is newtons. So that's how you convert everything to newtons. You multiply by 1 over 1,000, right? Or move the decimal 3 places to the left, whatever you want to do, times 9.8. Okay, so this is basically question 5. Given this information, right? Basically the masses in grams here. I want you to compute the forces in newtons for F1, F2, and then this ultimately, I call it the equilibrium here, but it's really the corresponding force that we want to compute is a resultant force, right? Because we want to add these two together to get a resultant. It's going to be the same magnitude, but opposite direction. And again, I explained that in the video, that short little video on the Kennan force platform, right? But you just have to worry about the mass in grams here. So convert to kilograms, multiply by 9.8, and that'll give you the forces. And then make sure you show me those calculations. Okay, question 6. Now on graph paper, what you want to do is you want to draw the vectors F1, F2, and R experimental with their tail starting at the origin. You want to do this to scale, so nicely drawn to scale using protractor and ruler, where the scale factor you want to use is 5 centimeters equals 1 Newton. Then you want to label the forces in newtons, the angles in degrees, and it should look similar to this figure right here, right? So I have F1, right? You have to draw the correct length. So how do you figure out how long to draw it? Well, if we know F1 is 0.98 newtons and my scale factor that I want to use is 5 centimeters equals 1 Newton, if I multiply by 5 over 1, right, 5 centimeters over 1 Newton, then that'll give me the correct length, which turns out to be around 4.9 centimeters. So I would draw at 4.9 centimeters, and using a protractor, I'd make it exactly 30 degrees. But then when you label your diagram, the graph paper, make sure you label the angle in degrees, and then make sure you label the force in newtons. Don't label it in centimeters, label it in newtons, right? You have to know how many centimeters long to draw it, but then label it in newtons. Do the same thing for F2, and then do the same thing for R, right? And it'll look something like this because it ends up being like 93 degrees. So it's a little bit past 90 degrees. Okay, and also in my sample lab report, I basically do this one for you guys. I mean, you have to do your own graph, but I do it out so you kind of have a good idea of what it should look like. Okay, question 7. Using graph paper again and a protractor and ruler. By the way, if you don't have graph paper, you can always go online and do a Google search for, graph paper PDF, and there's many free versions of graph paper that you can just download and print. So what we want to do now is we want to find the resultant vector using a different method. Remember, this method right here is using the Kennan force platform. That's what we got the data for. So this is like my experimental resultant vector. That's why I call it EXP, experimental. Now I want to find it graphically, right? Or you guys are going to find it graphically by adding the two vectors using graph paper. So you're going to use the triangle method, right? A vector addition, tip to tail. Use the same scale factor, and I give you all the directions here. Draw F1 first, starting with the tail at the origin. Then you draw F2 starting at the tip of F1. It's in the diagram here. What I would do is draw F1 first, right? So exactly 30 degrees, the correct length, 4.9 centimeters, but then label it in newtons. Then maybe draw like a new coordinate system at the tip of F1. Then you can draw F2. So here's F2. It's at 120 degrees. You would draw at the correct length. And and that's it. You just draw F1 plus F2. Then to get your resultant vector, I'm calling R graph because it's the graphical method. Remember, to get that, you just draw a vector from the origin, so from the tail of F1, from the origin, to the tip of F2. So that would be that vector right there. Now, how do I get its magnitude? Because I need to know that magnitude. Well, you would measure it with a ruler, right, in centimeters. And then using your unit conversion factor again, you know that 5 centimeters is 1 Newton, you can convert back to newtons. Basically, you would divide by 5 in this case, or multiply by 1 Newton over 5 centimeters, which is the same as dividing by 5. So to get the magnitude, you're going to measure it and then convert back to newtons, right, by dividing by 5. And then how are you going to get the graphical angle here? just measure it with a protractor. So when you do this nice on a graph paper, you can measure that angle with a protractor. Okay, then once you've done that, then I want you to compare. So you're going to compute 2% experimental errors. You're going to compute a percent experimental error for the magnitude, right, in newtons. And do this in newtons, not in centimeters, right? Make sure it's in newtons. And then you want to compute the percent experimental error for the angle, for the direction. So how do we find error? Remember, it's always experimental minus graph, but it's absolute value divided by the gold standard one or the accepted one. And we're going to assume the graphical one is the accepted one today. Okay. And then same thing for the angle. Your theta experimental, which was 93, minus whatever you got when you measured it on your triangle method, divided by your triangle method one times 100. Show me those two calculations and fill in the table here. Okay, great. Now, if you're in Physics 206, that's it. That's all I'm going to have you guys do for this lab. If you're in Physics 207 or Physics 212, then we want to do a little bit more. So the next part is basically almost the same thing, except now we're going to add 3 forces together, right? So on the Canon force platform, I now have a mass of 100 grams at 30 degrees, 200 grams at 120, 150 grams at 220. And I want to add them all together experimentally to get my resultant experimental vector. So just like before, this is similar to the previous question. I'm going to convert these values from grams, the masses, to forces in newtons, right? It's really compute, right? Because mass and force are not exactly the same thing. I say convert, but it's really compute. So make sure, again, that you convert from grams to kilograms, and then times 9.8 will give you the force in newtons. So you're going to do that for all 4 here, for F1, F2, F3, and your resultant experimental. On graph paper, draw all these vectors. So F1, F2, F3. So now you're going to have your magnitude and force, and you have all the angles. And the resultant is direct opposite of the equilibrant. So I did it for you here. The resultant is going to be at 136 degrees. So use the same scale factor, 5 centimeters equals 1 Newton. All the vectors should be drawn from the origin, and then label them again, just like you did before, in newtons, and label the angles in degrees. Then using graph paper, right, again, in a protractor and ruler, you're going to add those 3 vectors together, so F1, F2, F3, using the polygon method, which is nothing more than just continuing with the tip to tail method, right? So you're just adding 3 vectors together now. And then to get the resultant, which I'm calling our graph, you have to draw a vector from the origin to the tip of F3, right? And that will give you our graph. Then measure it with a ruler, and convert back to newtons, right? And you can use the same scale factor, 5 centimeters equals 1 Newton when you're drawing all this out. Then, just like before, I want you to compare the magnitude. So the magnitude of the experimental resultant vector and the magnitude of the graphical resultant vector, and then compare the directions. So compute 2% experimental errors and show me those calculations. Okay, and then the last part, we're just gonna play around a little bit with another simulation from the PHET collection of physics simulations. So we're gonna go to the simulation. Let me do that now. Okay, so go to the simulation. You can start it by pressing play. And then we're gonna use the Explore 2D part of the simulation. So you wanna click on that, Explore 2D. Actually, what I would do is maybe center this now. So it's kind of just showing you the first quadrant. So if you click on the origin, you can center this a little better. So something like that. And for the first part, for question 13, we want to use the component form of vectors, which is this one. So this is like, this one is sort of like the polar form. It gives you the magnitude and direction. And this would be the component form. So we want to use the component form for the first part. And what you're going to do is you're going to add 3 vectors together. In the table, if you look in the handout, in the table, I give you the components I want you to have. So like A, right? If I bring A to the center, I want it so that it has an X component of -10, and you can read it right here. Well, it's 6 right now, so I need to move it sort of in this direction, right? -10, and then the Y component of 5. So I guess it's right there. So X component is -10, Y component is 5. Then you would bring B. Remember, we're adding tip to tail, so I put the tail at the tip of A. And now I want the X component to be 0 and the Y component to be -12. So it would be something in this direction. Something like that. Then you add C, right, given the correct, let's say, I'm not going to use the same values that I did in the lab handout because I want you guys to play with this. Let's say that was B, that's A, and let's say C is something like this. Oh, let's see if I can do it here. Oh, it doesn't want to add. Hold on. Let me do this. I don't know. Let's say C has components of 31 in the X and 16, positive 16 in the Y, right? So 31 this way, 16 up. And now I want to get the sum of those 3, the sum of A, B, and C, which I'm going to call S. So to do that, all you need to do in this case, and we're just kind of playing around with this, you don't need to do any work of your own. You can just do it all in the simulation. Just click on sum here, and then you can drag it so that the tail starts at the tail of the first one, right, at the origin, and the tip goes to the tip of the last one. So I'm adding A plus B plus C. So this is basically the polygon method, right? I'm adding tip to tail. So I'm getting S, and then you can read off the values. So in the table, I want you to give me the X and Y component of S, and then the magnitude, so that'd be the length of this, and the direction, that would be the angle from the positive x-axis. So in this case, it's positive 13.4. By the way, if you, let me click off of this. Let's say C was this instead, right? And now I do the sum. Now, if you look at this, the angle is, go back to this S. The angle is -36. Well, what does negative mean? It just means that you start at the positive x-axis and you measure clockwise instead of counterclockwise. Normally, you measure counterclockwise. So you can either say that it's -36, or if you do 360 minus 36, that means going all the way this way. So 360 minus 36 is what? 324. So you could also say it's positive 324. So -36 and positive 324 would be the same thing, okay? And then in the second part, I want you to use the magnitude and direction form of the vectors. Again, I would center this. And then I give you, you know, D, I want a magnitude of 16. So start at the center, and an angle of 20. So let me get rid of the sum. You don't need the sum yet. So magnitude is 16. So now I'm looking here, right? The absolute value is another way of saying magnitude. So 16 and angle of 20. So perfect right there. Then you add the next one, E, and use the correct magnitude direction, whatever it is. And then the same thing, F. Let's say it's like that. And then if I do sum again, then I can read off the values, right? I can read off the X and Y components of that sum, and I can read off the magnitude and direction of that sum. So you're going to do the same thing, except I give you particular values that I want you to use in questions 13 and 14 from the lab handout. Great, and then that's it. then again, you probably want to look at, hold on one second, let me go back to the, okay, so again, you want to use these particular values that you give you for vectors A, B, and C, and then for vectors D, E, and F, and that'll be questions 13 and 14. Then make sure you look at my sample lab report, because that's what I'm expecting you guys to turn in, something that looks like that. Of course, I didn't do everything for you, but I gave you a good idea of what I expect. Now, again, remember, these are going to be group lab reports, right? Typically 3 people per group. So everyone should work on this, right? You want to, sometimes students will want to split things up a little bit, but make sure you're familiar with all parts, because when it comes to the lab exams, you're all going to be responsible for all the information. So make sure you kind of, you're familiar with all parts of the lab report. And then just one person from your lab group will submit the lab report on Brightspace, right, through assignments, activities and assignments. I will grade it, right? Make sure you submit it as a PDF. I will grade it and then send it back to that same person with a grade from 0 to 10. And then you can, whoever submitted it can distribute it to their lab partners. Okay, and we'll do that throughout this semester. All right, great. I know that was long, but hopefully that will be helpful. Again, most of you will be in class, so you may not even need to watch this. But those who are taking it remote, you definitely want to watch this video. All right, thanks, and I'll see you guys in a little bit.